Next question. Here we go. True or false? When we standardize a normal set of measurements, there's a keyword right there, normal. The data set has to be normal. And if it's not normal, this ain't true. But if it is normal, this is true. Remember that. So if you standardize a data set, let's pretend you had 10,000 pieces of measurements in there somewhere. And if you standardize them all, right, the mean will have a z-score. That's what the z stands for, the standardized score. The mean will have a z-score of 0, and the standard deviation will be 1. That is true. And I'll put the link in there where it shows you that's true. Now, we're going to go ahead and apply that for the next question. We got twin brothers, Jim and Tim. So Tim scored 650 on the SAT, and this is their distribution. That's how you read that. The capital N means the data set is normal. The first number is the mean. The second number is the standard deviation. Okay. But then his brother Jim took the ACT. He did not take the SAT, and they scored completely different. Of course they did. And here's their information. Right? Again, the data set is normal. Their mean is 17 with a standard deviation of 2. And Jim got a 20. So let's look up the formula real quick. So how do you calculate a z-score? Z-score. There they all are right here. So we're just looking up the actual formula, and there it is. Okay, so this x sub I is the individual score. So one is going to be for Tim, and the other one's going to be for Jim. And we know the means and standard deviations given from the process. So let's do it. Show up here, you. Come on, get in there, boom. All right, so the first z-score for Tim is going to be his score, 650, minus the group mean of 560. So that is 90 on top, divided by 60 on bottom. So 90 divided by 60 is 1.5. So remember that. Tim, his z-score, his standardized score, is 1.5. Switching to Jim. So Jim, the top of the fraction, his z-score is going to be, top of the fraction, 20 minus 17, which is 3, divided by the standard deviation of 2. 3 divided by 2 is 1.5. So they both got 1.5. So they tied. That's how that works. All right, moving on. All right, IQs are normally distributed. Again, normally is important. But they give us the mean of 100 and a standard deviation of 15. According to the central limit theorem, that's about the only theorem there is in statistics. If we did a sample of 100 people, what would the standard error be? Now remember, the standard error is related to the standard deviation with a little bit of difference, right? Standard errors are from samples, where standard deviations are supposed to be from populations. So the theorem basically states this, that you take the standard deviation from the population and you divide it by the square root of the sample size. So the sample was 100. We're going to take a square root of 100, which is 10. So we're going to divide the standard deviation of 15 by 10, and that's going to come out to be 1.5. That's the standard error. Next question. Looks like a confidence interval question. Okay, so we have 100 eighth graders. Remember that, 100. That's your sample size. Their average was 103.6 with a standard deviation of 14.8. Okay, that's good to know. Assume the scores were normally distributed. Again, that normality stuff is all over the place. And we want to make a 95% confidence interval for the true population mean. In other words, we are trying to track down the true population mean using this sample of 100 eighth graders. And it's only going to be 95% believable, right? Confident of 95%. So hopefully it'll be in there somewhere. But now let's look at the formula for confidence intervals. Boom, there it is right there. So this is the confidence interval page. So basically we're going to find the mean, which we already know, and we're going to add it and subtract it, right? We're going to plus and minus it to the margin of error. Margin of error, how do you do that, you say? Well, it's in there somewhere. It's right here. Here's the formula. Right? So confidence interval equals the mean plus or minus the z-score. This is the part that confuses everybody, including myself. The z-score reflects what confidence interval you want. We want a 95%, right? So we know the standard deviation, we know the sample size. So the rest of this stuff we can calculate. So let's figure out what a z-score of 95% is. There's that handsome rogue in there. Let's find out what a z-score. Again, there's the formula. Oh, there it is right there. 95%. So if we're looking for a confidence level of 95%, we're going to use a z-score of 1.96. Got it? 1.96. So let's go back to the problem. And we're going to build it. So the mean we know is 103.6. So they're all right on the first part. Standard deviation of 14.8. So we're going to take 14.8. Let me pull up my calculator. So 14.8. And we're going to divide that by the square root of the sample size, which was the square root of 100, which is 10. And that should be 1.48. And then we're going to multiply it by that z-star score number, which was 1.96. Don't forget that. So times 1.96. Now this value is your margin of error. So 2.90 is your margin of error. So that's the right answer right there. So again, we took the mean of the data set, and we're going to add 2.90. That's going to be your high value for your confidence interval. And then 103.6 minus 2.90, that's your low value for the confidence interval. And we're roughly 95% sure that the true population mean would be between those two values. Okay, that's how that works. Okay, next. Oh, great. Sample random of hen's eggs have the following weight in grams. The short answer is they want a 95% confidence interval of the true population for the chicken eggs, for the man's eggs. All right, so we need to calculate the mean and the standard deviation and the sample size. So give me a second. So I cleverly cut and pasted it into an Excel spreadsheet. So I'm going to find the mean like we did before. Click, average. Now here's something cool that Excel does. You simply highlight the data, right? And it knows not to answer those blank ones right there. So boom, there's your mean. Let's make it bigger. And I only want 2 place values. Now standard deviation, I click that cell, I go to the function bar, make sure I'm in statistical, and we go to Saint Deb with an S. Same thing, I'm going to highlight all the data. And boom. So let's make that like that. Boom. And there, there's even a count function on there, but we're not going to use that. Let me get this down to 2 place values. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, right? There's 8 per row, 4 rows, 32, 33, 34. So N is 34. So we're going to build our margin of error, which is, it's going to be, I'm going to show you some fascinating stuff. I'm going to type equals. So that tells Excel that the next thing coming is a formula that I'm going to make. So I want them to take the standard deviation, right? And we're going to divide it by the square root of the sample size. So let me show you how to do that. You put in a parentheses and you pick the cell that's got the sample size. And then you put that caret, that's the shift 6, the little thing that looks like a less than or equal, or I'm sorry, less than or greater than, but it's pointing up. And then we put 0.5, which is what the square root is. And that's going to give us our standard deviation divided by the square root of sample size. And then we might as well just multiply that by, well, here, let's hit enter. And now I'm going to multiply that by the 95% z-score, which again was 1.96. So I'm just going to hit equals. I want that number, and then multiply is Shift 8, the asterisk, and then I'm just going to type in 1.96. And that, ladies and gentlemen, is our margin of error. So we're going to add the mean, so the high value, and the low value of our confidence interval is simply going to be, I'm going to go back up to the function bar, hit equals. It's going to be the mean plus this number. That's our margin of error. And again, we're going to do the same thing. We're going to go equal sign, and we want the mean. This time we're going to minus the margin of error, enter. So those are our highs and lows for our 95% confidence interval. Let's go back and look at it. So 28.5, 29.8, 28.5, 28.5, 28.5, 28.5. Ooh, that one's pretty close. Let's go back and take a quick look at it again. Yeah, 28.54 and 29.83, and it's winner chicken dinner. That's your winner right there. So that's how that works. So which of the following is a correspondence level for critical z-score of 1.96? Now, you should know that 1.96 is very, very well used in statistics. That's your 95% rule. So if you got a critical z-score of something that gives you 1.96, that's got to be the 95% rule. Boom, that's that guy right there. All right, next. Critical alpha values, that's the one you reject the null with. Normally it's 0.05. It doesn't have to be, right? If you were working for a pharmaceutical company, they're not going to want you to cut off the values of 0.05. They're going to want you to cut it off to like 0.001, which means that whatever's there is going to be really, really, really strongly proven to be there. So this is true, though, because if it's not mentioned, right, that's what the question is. If it's not mentioned, we always assume it's 0.05. And again, we're one of the social sciences, so we get to get away with that stuff. And then the next question, get over there, you. True or false? Critical alpha, which is always usually 0.05, plus the confidence interval equals 100%. That is true, right? So think of it. The confidence interval plus the alpha has to equal 100%. So if we only had like a 90% confidence interval, God knows why you want to do that, but some people do, then your alpha has to be 10%, right? Because 90% plus 10% equals 100%. This is a good place to stop this video, and then I have one more that'll handle the next couple of questions. All right, keep up the good work.